Hello everyone, welcome to this week's Chrome seminar. We have two speakers this week. The first speaker is Professor Amir Barati Farimani from Mechanical Engineering Department at Carnegie Mellon University. So before joining CMU in fall 2018, he was a postdoctoral fellow at Stanford University. Professor Farimani has broad research interests in the application of machine learning, data science, and molecular dynamic simulations to health and bioengineering problems. His lab at CMU is a multidisciplinary group, and its mission is to bring the state-of-the-art machine learning algorithms to mechanical engineering problems and applications. So without further ado, welcome, Professor. You may want to start.
Yeah. Sure. Thank you very much, Zongren, for the invitation, and also George. There are a lot of familiar faces here, and I think I should have done this sooner, you know, with the great intelligent people at Brown. And we have a lot of things in common with your lab and your group. So I wish to come back and talk about our recent developments also on the operator learnings. I mean, we recently published a preprint on transformers for the operator learnings, which is very interesting. And I think it will be very interesting to most of you. But today I'm going to talk about, you know, the molecular stuff. So, and molecular chemistry, the stuff that actually heavily my students, Young, who is here, was involved in and did an excellent job in you know, pushing the SOTAs more forward. So today I'm going to talk about molecular, I mean, the kind of methodology that we have developed, which is called molecular contrastive learning of representation. And essentially the reason that we do that and the motivation is that in drug discovery and any molecular task, I mean, the prediction of the property is very important. And the prediction of the property of molecule is not an easy task. You need to run a wet lab or run, for example, density functional theory or molecular dynamic simulations or a lot of calculations to get the labels or prediction for one molecule. And then as far as drug discovery is concerned, essentially the space of search for the molecule is humongous. So as you can see here, for example, the size of potential pharmacologically active molecule is estimated to be 10 to the power of 60, which is a humongous space. And we don't have obviously labels for all these significant number of molecules that you can build based on the periodic table. And on the other hand, as I mentioned to you, creating the label either experimentally or computationally is very, very expensive. And as you can see, for example, for one of the data, or one of the databases, you can see that there are only like, I mean, these red points here that you have the labels, and there are huge number of trees and branches of different kind of molecule substructures that we don't have any labels. And we want to predict them, and we want to, in a kind of like fast way, right? I mean, in a kind of very, very rapid way. And here also, I mean, on the right side, you can see the magnitude and the size of big data sets that are available. For example, on the molecules, I mean, that you can create here is 166.4 billion molecules with 17 atoms of only C, N, O, S, and halogens. And this is by far the largest small molecule database reported to date, called GDP17. So this problem, which is the problem of essentially predicting the label, is a very fit problem for machine learning, right? And because we want to have a fast surrogate models that are very, very good in predicting, at the same time saving us time and, you know, effort for the molecular discovery, either for drug discovery or for other properties of interest. And that's why, I mean, there's a huge interest since 2012 that actually the new rise of AI came into play. There's a huge effort in molecular machine learning as well, lots of startups and things like that. So another motivation for our work is that really it's very difficult to present the molecules, right? I mean, molecules, structure is not like images, right? I mean, in images, you have pixels, and pixels are structured data representation, but molecules are usually are very unstructured, right? I mean, you may have a very long tail of alkyl chain, right? I mean, for example, look at caffeine molecule, the molecule of interest to all of us. I mean, you need to have a representation, or you create a representation that is able to encode, right, the information that is contained in this molecule as feature representation. And as far as machine learning is concerned, I mean, feature representation is very important, right? And there are ways to represent, right? I mean, for example, we have a smiles, we have a smart, we have selfies, which most of these are, they are failing, I mean, to encode the topology information, or to some extent the chemistry information directly. And that's something that is an active area of research, like how you can efficiently transfer the information from a molecule to a feature space or representation space. So that's a topic which is very interesting, and also an active area of research. Since 2014-15, and before that, obviously, there was this idea of, like, I mean, if you look at the molecules, I mean, you can just say that, oh, wow, this is very similar to a graph, right? I mean, essentially, graph representation is quite a great fit to molecular space, right? Because if you look at this, for example, molecule, you can see that you can assume that nodes, atoms are nodes, and essentially bonds are edges, right? And so that's the definition of a graph, G and V and E, right? G as a function of V and E. And then the question is that, okay, if you want to use the graph formalism here, so what is the best way to couple the graph learning, with the feature representation? So that becomes a new question. And in general, usually I give this left side, pitch here, that what are we after in molecular machine learning? And obviously, most of you know about this. I mean, this is not it's no brainer, but essentially you have your X, which is the molecule, and you have the Y, for example, you have a property like solubility, right? And you train on, for example, a set of molecules for this, and that's your training. And then on the test, you are giving a new molecule with a new structure, and it is the notion is to predict the properties of this molecule, okay? So what's the properties? And there are obviously classification and regression tasks, as all we are aware. For example, toxicity prediction is a classification task, because you say if a molecule is a toxic or non-toxic. But solubility is a regression task, because essentially you measure, or you're predicting how much soluble, for example, a molecule is in water. And as I mentioned, like, it's a natural fit to use graph neural networks for the representation. And most of you are familiar with the graphs. I mean, they have nodes and edges, and there are different functions like aggregation of the nodes and message passing, and combining and reading out, which we call it pooling in the image terminology. And so in general, I mean, graph is a great representation. And as I mentioned, I mean, there is this notion of graph neural networks versus, for example, simple neural networks, in which actually you learn the representation using graph neural networks, and you parameterize, or you adjust the weight of a neural network that is represented by a graph. And there are certain, they are not problems, but there are certain actually functions that are needed, I mean, in order to assemble these neural networks. For example, one of them is pooling on the readout, and that is, for example, addressing the challenge if the molecule input, the size of the graph is different. For example, it has 8 nodes versus, I mean, another molecule has 20 nodes. So what should we do? Because the size of feature space is changing. So we have pooling, for example, max pooling or average pooling on the readout operation, which we level off on the feature space. So there were a lot of efforts that I'll talk about in the graph neural networks and graph convolutional neural networks, essentially, in which you learn also the filters, like, I mean, as you learn in the convolution operation for images. But also I wanted to talk about a recent rise of self-supervised learning methods in general in machine learning for computer science, in image processing, in images and vision and NLP. And that's the notion of self-supervised learning, in which actually there's a significant effort in the way that we learn the representation via supervisory signals that are coming from the data. So, and the way that self-supervised learning is working very efficiently is that in the optimization landscape, you are not starting from a very far away from the local minimums or global minimums that you are after. And then essentially you have some help on the learning of the representation with the data that is not necessarily labeled, right? So you can learn, for example, I mean, we have a lot of molecules, as I mentioned, like 166 billion molecules, that we have their structures, and we can learn the structure, right? Via self-supervised learning, in which you don't need a label, but I mean, you learn the structure of the molecules, how they are resembling into each other, how they are differing from each other. And that's the notion of self-supervised learning, essentially learning the representations and learning the supervisory signals from the data. And this is called learning the underlying structure in the data, and it has a lot of benefits. I mean, from the mathematical standpoint, on the optimization landscape, it is much closer to the target, whatever property you want to predict, either regress or classify, and that's a huge advance actually in the field of computer vision for machine learning. Another technology that became really interesting and method back in 2020 by a paper again from Jeff Hinton lab is the notion of contrastive learning, which is coupled with the self-supervised learning notion. So in which, I mean, if most of you are familiar, for example, generative predictive models, in which you have data and you have a label, or you generate either the data labels or you are generating new data. But there is another way to look at it from the representation learning standpoint, is that you can create different instances of data as an input on the right side, right? And you can say that you can classify, right? I mean, or you can say to what extent these data points are close to each other or they differ from each other, right? So you can create a loss essentially for the contrastive learning and learn the similarities between or differences between these instances of the data, which they may or they may not have similar labels. And then essentially you can learn the underlying structure of the data, which is a very cool idea. And to explain the contrastive learning for images, the paper from Jeff Hinton's lab, which I brought it here, the idea is like this, that for example, you have an image of a dog, as you can see here. You can augment it, right? The original is A. You can crop and resize. You can crop, resize, and flip, or color distort, or I don't know, all these operations that you can do in order to augment the data. And essentially, all of these are still a dog, right? I mean, if you want to do the contrast, all of them are still dog, but I mean, it's like a big exercise for the network to learn that, okay, if the dog is rotated or some part of it is cropped or it's blurred or there's a Gaussian noise or Gaussian blur or any kind of filter, essentially they are the same. So on the, and how you can compare this, the best thing is to run your CNN neural network, GNN or whatever, and create the representation, and then essentially contrast them or say how much similar on the latent vector or on the latent representation. So latent representation is a great way in order to compare and contrast the similarities or contrast between instances. And we know that this is, all of this is a dog, for example. And also we know that, for example, this chair, I mean, the way that you augment it, you change the color, you change, the background, everything is still a chair, right? So these two are similar to each other. These two are similar, but I mean, for example, a chair is completely different from a dog, right? So they repel each other. And as you can see here, the loss function for the contrastive learning is essentially is a kind of like cross entropy loss, in which it is running on the exponential of the similarity between the two instances from the latent vector, normalized by a temperature hyperparameter here, and then divided by the sum of all these actually levels of energy that you get here. So this is called contrastive learning framework. It is on top of the self-supervised learning. It is a subclass of self-supervised learning because you learn the representation, as I mentioned to you, based on this. So now let's go to the methods that my student Yu Yang, who is here, has developed along with the other students in the lab. And it is inspired, as I mentioned to you, by contrastive learning, combining it with the graph neural networks, and again, combining it with the ideas of self-supervised learning. So all of this will come together. But I mean, for migration from image space to the molecular space, obviously, the first thing that comes to my mind is that how you can augment the molecules, right? I mean, so for images, you can distort them, you can rotate them, you can add noise, right? I mean, you can flip them, you can, crop them. But what can we do with the molecules? So that's an interesting question. There are ways actually that you can augment the molecules. For example, these are the three different techniques. I mean, one of them is, as you can see, atom masking, that you can mask the atom. There's a level, obviously, you cannot go, it's very dangerous to go very wild on the atom masking because it is transforming the molecule, but to some extent, which is a hyperparameter, is acceptable. Bond deletion, right? I mean, obviously, you can delete some of the bonds without hurting too much. And subgraph removal, for example, you can remove a complete subgraph. And these are different techniques that you can essentially augment the data. And now that we have this augmentation, so you can essentially compare to the contrastive learning framework for images, what you can do is that you have the SMILEs of the molecules, you will augment them and create different kind of instances, as you can see in the left-hand side, right? And then you build the graph convolution on top of them, learn the representation, and then essentially you have different latent embedding of each molecule that is augmented. Here, as you can see, H1 up to H2N, and then essentially you can parse it, or you can connect it to the contrastive loss, and then you can say that, for example, these molecules that are augmented are similar to each other via the loss function, and the molecules that are, for example, different, they are repelling each other, or they are not equal to each other. So you can do this, I mean, on many molecules, right? And essentially you don't need labels, right? I mean, which is a big thing in the molecular space, because I mean, having the data sets with label is very difficult. And these are the augmentation techniques that in B you can see, I mean, we did. And then this, the molecular actually has two stages. So the first stage is training it on labeled databases, which is around 10 million molecules. So you train actually the weight of your neural networks, graph neural networks, with 10 million molecules unlabeled. These are augmented essentially with these three techniques. And then you do the contrastive learning, and your graph neural networks here is trained to learn the representation. And then you wanted to do a task which a labeled data set. For example, you wanted to predict toxicity, or you wanted to predict solubility as a regression task. So what you do is that you share the parameters, right? You copy the parameters that is represented here or learned here via pre-training, what we call, and then you send your labeled data and you call it fine-tuning, downstream fine-tuning, because from the landscape optimization landscape, you are not starting from ground zero, like initializing the whole weights. You can start from somewhere that the representation is fully learned. Now you adjust it a little bit to go to learn the properties and attach the properties to the feature learned representation space. So this paper is in Nature Machine Intelligence in 2022, and you can read it. I mean, the codes and everything, the scripts, the benchmarks, everything is on GitHub, available on the GitHub page of the lab. So feel free to use it. And then I just wanted to explain a little bit more about the contrastive loss, in which in the contrastive loss, essentially the intention is to maximize the agreement between positive samples while minimizing the agreement between negative samples. And what we mean by positive and negative, the ones that are similar with each other via augmentation are obviously similar, but there are two molecules, two of them are augmented, but they are completely different, so they are negative actually samples. And as you can see here is the contrastive loss. We call it the normalized temperature scaled cross entropy loss, NTXNENT. I mean, that's the way that usually we talk about it. So let me go a little bit over the training details. Each atom is embedded by its atomic number and chirality type. These are the features that you can load. Obviously, RDKit and other softwares that we use, for example, for molecular preparation and pre-processing, they have a lot of different kind of features that you can load on top of your graph. But essentially, these are the features that we thought, I mean, are really good. I mean, like atomic numbers and chirality type, while each bond is embedded by its type and direction. So that's the way we are using. There are different ways that you can use. There are different graph neural networks these days for molecular machine learning. One of them is graph isomorphism network, GIN, which has a ReLU activation, is implemented as a GNN backbone. So we actually benchmark both of the GINs versus classical GNN, and I'll show you the results, how it is working. We use average pooling to the readout operation. So in the molecular machine learning, I mean, we call it readout operation, but this is essentially the latent vector, if you're feeling more comfortable with that terminology. Batch size is 512, feature dimension is 512, and usually, I mean, in also molecular world, we are using optimizers, add them with the learning rate of e to the power of -4. We pre-train for 100 epochs. Obviously, this needs a lot of resources. We have A6000 GPUs and other types of GPUs, which you can train actually on large data points. First of all, I should say that these are the classical benchmark data sets. I have a slide further down the road, but I mean, these are really important data sets that everybody benchmarks, and it's like an Olympics, right, of SOTAs here. I wish we had such kind of thing in the world of partial differential equations and turbulence and other stuffs that your lab and my lab we are doing. But this is great because I mean there are different kind of benchmarks, and you can benchmark against and see how good you are in many terms. So there is this for example data set for triple BP, toxicity tox21, clean tox, HIV, base and cider, and MUV, and there are different tasks. For example, MUV has 17 different classification tasks, cider has 27, tox21 has 12 tasks, so they have different multiple tasks also, but all of them are classification. I mean, this table is about classification, and traditionally, for example, random for shallow machine learning methods, usually folks in the area of molecular machine learning are reporting it on the left side, RF, SVM, And here the classical graph convolutional neural networks and graph isomorphism networks, SNET, MGCNN, and DMPNN. I mean, these are, I mean, the reason that we have a line here is that these are the methods that are supervised learning, completely supervised. And the methods here, they are using pre-training, I mean, below this line, Hu et al., which is from Ure and Vijay's lab at Stanford, and other works. And the two last ones are the molecular, the methods that we develop with the contrastive learning and pre-training. And then for the backbone, we use the GCN, and also we use the GIN, and you can see the results. For example, in some places we are not SOTA, but for example, for TOX21, we are really good on the compared to the self-supervised learning methods, and also other ones. For example, for the clean tox, we are SOTA across all of these samples. For base, we are SOTA. It's not like that you get SOTA everywhere. And that's an interesting thing, you know. When you sometimes, I mean, you gain something and sometimes you lose something depending on the nature of the data sets and things like that. But overall, it's very competitive, actually, the methods, as you can see. For example, for MUV also, we are far away, and we are really good in the SOTA regime. Also, we tested it on the regression.
Amir, can I ask you a question?
Sure.
So if you compare with one of the in the previous table, for example, the gram, the n-gram, because that looks pretty competitive. Can you say the difference? What gives you? What are the main differences between n-gram and your method?
Yeah, I think, I mean, Yu-Yang, do you want to answer that? I mean, let's get Yu-Yang involved.
Okay.
Yeah. Yu-Yang?
How can you hear me?
Yes.
Yeah, sure.
Yeah, so I guess the question is like, what's the difference between molecular and like GCMGM?
So the question is that for the n-gram, which is the self-supervised,
okay,
compared to the molecular.
Yeah, so the thing is, say in n-gram, what they do is they design a graph embedding using the shortest work based on the molecular graph, and then they apply, say, random forest or any other machine learning methods on top of that to learn the features. So it is a, I would say, self-supervised or unsupervised baseline model we compare with. And for Hu et al., in their case, they are using two-level self-supervised learning task. One is the node level, where you randomly mask out some atoms, and you predict the attribute of the mask atoms. So that's what they call atom level. And the second thing they design is the graph level pre-training task, where they where it is pre-trained in the actually supervised learning manner, where you fit in the molecule and you predict the certain properties. And by this means you can learn some reputation. So that's the difference. And in our work in molecular, what we're doing is, as Amir mentioned, we're doing contrastive learning as the pre-training. So these works actually differs in the pre-training techniques, I would say.
Okay. But
thank you, Yang. Yeah, on the pre-training, George.
So the pre-training, yeah, so that's what I thought. Yeah, excellent.
Yeah, thank you. So yeah, and also, I mean, for the regression test, you can see, I mean, our benchmark. For example, I think, I mean, we have a larger table in the main paper. I mean, we have also all different QMs. I'll show it later. For example, SNET, I mean, is really well designed for the QM9. I'll show that results later. But you can see, I mean, we are also in a good space, I mean, for molecular compared to the other methods that are supervised and self-supervised. So we also did ablation, a few ablation study, for example, for the cross-entropy loss, I mean, which is normalized by the temperature parameters. You can see that you can put different levels of temperature here, tau 0.05, 0.1, or 0.5. And then you can see, I mean, you get really different results, I mean, compared, I mean, so this is a hyperparameter that you can tune. Also, we did ablation study on the augmentation. So by augmentation is that, for example, what is the effect of subgraph removal, atom masking plus bond deletion. So you can see that it significantly changes the results. For example, for ClinTox, you can see atom masking plus bond deletion is at 85%, but you do the subgraph removal, I mean, you get like, I mean, a huge actually enhancement, for example, there. And all of these are raw KUC. Then another things that we did is, for example, on the supervised learning task, I mean, this is the graph isomorphism neural networks with and without molecular graph augmentation on all the 7 supervised molecular classification benchmarks. And you can see without augmentation, essentially for the triple BP and talks to anyone, especially for triple BP, you can see, I mean, 65%, around 65% without augmentation, but while you do the augmentation, it is going to 72%. So this is the effect of augmentation without self-supervised learning. So we wanted to show that even if you don't do pre-training, I mean, even only if you do also augmentation, I mean, your learning will enhance. So augmentation is very important. So what you can do essentially to say that how good the representation of the molecules have been learned is that to run a testnet on the embedding, right, of the molecular representation that you get from the latent vector, and you can essentially embed it. You can represent it here, and then you can color, for example, the two-dimensional actually plot of testnet with the molecular weight. And what you can get out of this visualization is that usually if a representation is learned very well, you can see a cluster of molecular weights. And you can see, for example, some of the molecules that their molecular weights are similar are clustered with each other. The blue ones are clustered with each other. This is a very type of fuzzy type of image in the representation learning, but it shows you some signals that how representation is learned. Or for example, here, this is on the pre-training again for the free solve and how actually some of them are separated. This is another example of, for example, for the representation on the molecular pre-training, and the color of each embedding points indicates the marketed drug and adverse drug reaction from CIDR. So this is the CIDR data set. Like a few months ago, we thought of different ways that we can improve even molecular further by using a framework that I'm going to explain to you. And this paper just published, in JCIM, Journal of Chemical Information and Modeling. This is an article ASAP, and we called it Improving Molecular Contrastive Learning via Faulty Negative Mitigation and Decomposed Fragment Contrast. And again, Yu Yang is the lead work here, lead actually author here. As I mentioned to you, I mean, in the molecular idea, I mean, we have different, augmentation techniques, and then the contrastive learning that they repel or they are similar to each other. Here in the iMolecular, actually, the innovation that we had is that we changed the loss function into a kind of weighted cross-entropy loss in order to eliminate the faulty negatives. And another innovation and techniques we use is something called substructure contrast for molecular motifs, which I'll explain. So for the contrastive learning, again, I give a recap that you augment, right? And you say that since these are coming from the same molecule, they attract each other, but these are the two different molecules, so they repel each other, right? And although you augmented them in the latent space. So the intuition is based on this, that you have, the ones that are similar into each other, they are attracting, and they are repelling the ones that are not similar. And this can be seen in the normalized temperature scale cross entropy loss. Now, the idea here is that for something that we call it faulty negative mitigation, you can define a molecule or sub-molecule called anchor, and then you can augment it, right? Or you can actually have different instances of that. For example, this MB compared to MA and compared to MC. And then essentially there is a level that these three molecules are different, right? I mean, for example, the molecule in the middle is very, very negative compared to the right one, but it is very similar. It's not that much negative compared to the left one, right? MA and MB are somehow much more similar compared to the right one, MC. And this is what we call it faulty negative. And then we have some ideas called faulty negative mitigation, in which what we can do is that we can have a measure of how close a molecule in the representation space or in a latent representation is to the anchor molecule compared to the negative sample. So how we can reflect that into the weighted cross entropy loss, essentially we change it to the weighted cross entropy loss by defining a similarity between the two instances that we have and embedding that W sub ik here as essentially measuring how much negative, or a kind of like a spectrum of how different two molecules, or how negative they are, or how positive they are with respect to each other. So how we do that? So essentially you can see that here in the original loss, I mean, we just directly go and find the cosine similarities on the latent space, which is pretty common even with the attention models. This is like, I mean, the way that people measure the differences. But here also we weighted that similarity by using the chemistry or the concepts of fingerprint similarity, which all of you are familiar with, for example, Tanimoto similarity and ECFP fingerprint, in which actually you can adjust or you can modulate this weight by molecular fingerprint, right? And you can measure the similarity by the Morgan fingerprint and put that essentially in the as the weight here, as you can see, FP similarity. And there is also lambda 1, which is a hyperparameter you can adjust later. There is another technique that we use, which is interesting, is called fragment contrast. So essentially you can break actually a molecule into different pieces and also say how much negative or how much positive or how much they are repelling or how much similar they are within each other. And that's a great opportunity to augment the data. So for example, you can break this molecule into two fragments and either do the fragment contrast within a molecule or between two molecules or between different kind of molecules. And that gives you this capability to enlarge, you know, the space of representation learning without any kind of need to have the labels of, for example, what these molecules are. For example, these molecules, I mean, so it is intermolecule and intramolecule fragment learning, and then so you can do a lot of actually cool stuff. And you may wonder, okay, for such kind of large molecular space, how we do it? So in RDKit, there's this beautiful, you know, decomposition technique called bricks, in which actually automatically it breaks the molecules into retrosynthetically interesting chemical substructures, and then you essentially label them that, oh, this is the same molecule, this is different molecule, and then you calculate the fingerprint similarity and you parse that as the weight into the loss function. So that's essentially, you are giving a lot of hint to the learning of the system during the pre-training. So as I mentioned, this is also, so you can do two things. I mean, you can have your own actually weighted cross entropy, and also you can create a fragment cross entropy loss, as I mentioned here, and then you can create a total loss, actually adding the total loss from the weighted cross entropy plus a hyperparameter multiplied by the fragment cross entropy. Again, the similar story as I mentioned to you for molecular, but here with all these, fragment substructures, faulty negative mitigations, the first step is that you have your huge unlabeled data bases, hundreds of millions of molecules you train, and you do the contrastive learning in the way that I described, and then you share the parameters, right? to the label database, whatever downstream task you want to do, if it is a regression or classification for the toxicity, for example, classification or solubility prediction, and then you actually predict the properties. So that's the standard way that it works here. So we pre-trained the data on 10 million unlabeled molecules from PubChem. The backbone structure is 5-layer graph isomorphism network, and the batch size is 512, feature dimension 512, optimizer is Adam, and pre-training is usually for 100 epochs. There are many fine-tuning details, for example, batch size. And these are the hyperparameters that you guys are also in any kind of architecture of neural networks you are doing. And then the benchmarks, as I mentioned, I should have done this earlier. At the time that I was in Vijay's lab, we created MoleculeNet, and then, these became the standard benchmarks. And here we are, right? Compared to the other ones, I showed you the ones before, it was molecular. Now we have iMolecular, which is the ones with the faulty negative mitigations. And you can see the improvements, for example, 3%, 1% sometimes. With clean tox, for example, we are becoming quite better. And at the same time, there are also other methods which are coming. For example, attentive FP is a good method that came in, but still, in the clean tox, we are SOTA, and still, like in many other places. And in overall averaging, so it's these days it's common that you do actually all these benchmarks, and they are extending. Like, for example, these days, journal reviewers and editors, once, for example, ToxCast, which is huge, it has 617 tasks, which is very big. And you can see even, we are SOTA on that, which is a lot of tasks here with 8,500 round like molecules, and we are 73%, right? So we are SOTA here. We are SOTA on MUV. We are SOTA on CIDR. On base, we are a little bit down, and the others, we are very competitive. CleanTox, we are SOTA. And on average, also, we are SOTA. So if you take the average over all the tasks. So here is the regression tasks. These are really important regression data sets and benchmarks. So FreeSolve, ESOL, LiPo, QM789, which all of them are interesting. So as you can see, for example, SCHNET, I was talking to you, SCHNET is really good, for example, for QM9 or
Amir, what is the regression task? Because I can understand the classification like the previous benchmarks. Can you describe what is the regression benchmark here and what's the sense of regression here?
Yeah, sure, George. So for example, for FreeSolve, essentially for ESOL, you are predicting the solubility of a molecule in water. So you have a molecule, how much it is soluble in water. So that's a degree, right? It's not like you classify. So you say that this is 0.7 millimolar solubility, or it's like 20% soluble. So that's the regression. Or in QM, for example, it is. All of them are DFT calculations, and they calculate, for example, the band gap, or all these measured properties that are, for example, conductivity, which
quantify a property, basically.
They are quantified properties, and most of them, like QMs are, all of the QMs, George, are DFT calculations, and ESOLs and others are experimental. So these are really classical benchmarks on regression. And pre-training usually sucks in regression because there is a reason for that. And we discussed this with Yu Yang and others quite a bit. And because, I mean, when you do augmentation, essentially you're changing the form of molecule, right? I mean, you're deleting a bond or you're adding you're masking an atom. So that is much more sensitive to the regression compared to classification, right? And also in images, it's like that, right? I mean, if you wanted to, for example, predict the age of a person based on the face of a person, right? That's the regression task. If you, for example, crop it or add more noise, essentially the guy may look older, right? But I mean, if you crop for example, dog versus cat, I mean, if you crop the tail or if you add more noise, Gaussian noise or whatever, it's not changing the classification, right? A cat is still a cat if you crop it. So that's the message, right? I mean, you can see that, I think, I mean, in future also we'll see that the pre-training self-supervised learning will really catch up and will become better and better on all these classification tasks. While, for example, a SNET, I mean, is a great method that always, I mean, like it's gonna stay there on the top in many tasks, or for example, MGCN.
So what are the numbers? The numbers here in the regression mean what?
So, so this is the mean and standard deviation of test RMSE.
Oh,
so
I see.
Yeah, it's the test RMSE, George.
Oh, I
Root mean
see.
square.
And it's MAE for the other ones. Okay, I got
Yes,
it.
yes, yes, yes. Yeah, it's actually, it's interesting, George. I mean, we should talk about this for the, PDEs and, other, it's really great in the scientific computation. Actually, I mean, the benchmarks like this, because everybody, even on the way that you split the training, we have a scaffold splitting versus random splitting. So if you do that, I mean, like a scaffold splitting, when you are doing the test train, the results significantly differ. And now it became a standard that you should do, for example, a scaffold split. So the good thing is that we have a lot of great standards in the molecular machine learning. QM9 is, for example, you asked George, I mean, what are the properties? For example, QM9 has 8 tasks, on 130,000 molecules. And this is the breakdown of tasks, So for example, HUMO calculation, I mean, for example, heat capacity, and these are the regression tasks. And you can see that per each task also, we are doing really good, I mean, we are sorting some are like 6 of them. It's only the test MAE on the QM9 benchmark. Again, ablation study with and without, fragment contrast and weighted cross-entropy, and you can see the significance enhancement, in many cases that we use, for example, so the left side is classification. Again, the right side is the famous, regression tasks. And there was this question that I asked Yu Yang, and he addressed that: does adding extra features benefit the molecular? I mean, so for example, adding charge of an atom or degree or chirality. We already had the atomic number and chirality, but I mean, RDKit provides a lot of different types of features that you can load onto your graph. For example, hybridization, I mean, you can have that type. And we found out that essentially atomic number and chirality plus bond type and bond direction, they have really good effects. And then to answer this question is, for example, with the original features, which are the 2 features, and with the enriched features, and you can see there is a small improvements, especially for a specific data sets like CIDR, but not overall. I mean, it's not a big deal. So I think, I mean, topology learning and is much more important. And then again, I mean, Yu Yang went ahead and he created a search querying based on the representation learning, and he proved that essentially this representation is very well learned, and you can use this to query, for example, this molecule and find out that the ones that are found out, and then you can go ahead and calculate the similarity of this molecule using the ECFP fingerprint, and you can prove that, wow, I mean, this is doing a good search. And I think, I mean, that's most of the things I wanted to talk about. And in conclusions, actually, essentially, we created this interesting framework inspired by the techniques that have been performed in imaging, in computer vision, like contrastive learning, self-supervised learning, and also the techniques that have already been developed, like graph neural networks, and then bump them together, reformat them, change the loss function, and then we were able to get a lot of SOTAs, you know, on different kind of benchmarks. So with that, I mean, this is my lab, and we are doing a lot of cool things. I mean, these are the current PhD students. Most of this work is done by Yang, the guy on the right bottom. I mean, he's here, and our lab is funded by some of the agencies, which I need to thank. Thank you very much, George, and all the great groups at Brown. I mean, it's my pleasure actually to talk to you. I mean, you're all great experts in these fields, and I wanted also actually to talk sometimes about, you know, I mean, this neural operator transformer things that we put it on archive. It seems it's an interesting work for learning PDEs. So hopefully later on, I'll talk about those efforts we did as well. Thank you very much.
Thank you, Amir. This is a great talk. This is a great topic also.
Yeah, thanks, George. I appreciate your invitation.
Have more questions for Amir? Lulu, this is a good topic for you to pick up there in UPenn.
Yes, it's a really great talk, and it's very inspiring.
Yeah, thanks, Lulu. I'm following your work with DeepXDE. You're doing an amazing work at UPenn. We should chat.
Menja actually in the audience is working with contrastive loss, and I think she's trying to also to modify it, but it's mostly for classification. And I'm not sure what application that she's doing.
Yeah, I mean, actually, George, I mean, as I mentioned, classification makes sense with contrastive learning, right? Because as I mentioned, because you do the augmentation with the, you know, for example, if you think about an image of a dog versus cat, right? I mean, you crop it, you flip it, you add a lot of noise. It's still, you can classify, right? I mean, even human. But I mean, if you wanted to, for example, add noise to our faces right now and predict our age based on our face, that becomes erroneous, right? So I think, I mean, in general, you're right. I mean, contrastive learning works better for classification. That's our observation too.
Menja, do you want to say how would you manipulate? You use a standard contrastive loss function, or you're changing it? I remember you were talking about it.
I think we have two projects using contrastive learning. The first one is not on classification. They just do, I just use it for actually the graph embedding learning. So, so during the graph embedding representation learning, and then we use the contrastive learning loss, like sample some positive nodes and negative nodes, like that.
Oh, so you're doing the similar things to us. Okay, great.
So Amir, this is kind of like node to vec, but she's doing G to G, what is it? Graph to Gauss with uncertainty quantification.
I see.
Yeah.
That's the first one. The second one, what is the second one, Menja? The second user.
The second one is actually we want to do some adversarial contrastive learning. Yeah, that's a unfinished project. Yeah. So like the paper of Hinton on the same
Sinclair.
The loss function they use in the. We want to study some the model theory stuff.
Cool. That's very cool actually to do that. You know, I mean, you can play around with the loss function, and you know, as far as physics informed, like I mean, the things that we did here some ideas here that you parse the weighted, negativity versus positivity using fingerprint similarity. You can do the same thing for the physics informed laws, right? I mean, so you can weight how much, they are differing on the physics space.
How much
I think that's a cool idea. Yeah, that's a cool idea to do.
No, that's a very good point. How much you deviate from mass conservation, for example.
Exactly, for example, and parse that, and then the network learn, exactly.
Yeah, SSL is the future. I have a question, Amir, on so this is all equilibrium chemistry, right?
Yeah.
In other words, the molecules are stable and so on, but how one could extend this to metastable states or non-equilibrium chemistry and non-Arrhenius chemistry?
Yeah.
You have this dynamic graph, so to speak, that could change at any moment, right?
Yeah, exactly. Actually, we did a work, called graph accelerated molecular dynamics. So that's just published in JCP. So you're right. I mean, these are bulk properties that are measured at exactly equilibrium. So in non-equilibrium, I think, that's a very difficult, actually, type of task, because you not only have this nonlinear mapping of the structure and property, but also you have the dynamic which is kicking in, and then that uncertainty plus this one, it becomes a huge difficulty. But also I wanted to send here the graph accelerated molecular dynamic. That is actually you can use graph for accelerating actually molecular dynamics simulation, in which I know that you and Narayan and others at some point you were really fond of doing a lot of MD simulations and DPD. So this work that George we did published just a month ago, it's about how to accelerate on the dynamics, how you use the graph on the dynamics, and then the message passing. Essentially, you're learning the forces, and then you essentially create a loss function which is about the forces, and you do regularization there, and we are able to create a very fast, actually, molecular dynamics simulator, which is bypassing the redundancies, right? So if you think about, for example, calculating the water, like doing MD simulation on water, right? There are many instances in the molecular configuration at instances at each time step that they're similar, right? But in the calculation, you're redoing the calculation. Also in the numerical solvers, you're doing a lot of repetitive solvers. I think, graph can learn those instances and speed up. So that's this work that we did in JCP. But back to your question, I think, that's very difficult non-equilibrium properties classification or regression.
Yeah, that's thanks for the paper, because I have another student, Chen Chan. I don't know if he's around, but he's trying to he's working on interactive particles. So we had another talk from England on how you can accelerate molecular dynamics. And
Max Welling or Niels Turi?
No, was a guy, Alexander, I think, is
okay.
Italian Greek from Warwick, I think. He gave a talk, and he has a paper under JCP, but there's some physics that I'm handling. So I knew it, and I invite him. So that so kind of similar spirit so we're interested in that. Thanks very much. Any other questions for Amir? Amir is working on. We will invite you back for the operators, because this crowd now is hot on operators. But we have today, although it's summer, we have 40 people from around the world attending your talk. So
that's amazing, George. The group that you assembled and the type of works, all of my students are following the works that is coming from Brown, and even our work. Our deep learning operator for the transform is also inspired by your original work, in DeepONet. So we heavily talked about and cited those actually works, and I would love to come back and talk about transformers, you know, I mean, for partial differential equation operation learnings. And you may have seen the preprint, but I just posted it here again. I mean, a few days ago we put it on.
Okay, great. Yeah, great. Let me just click. Thank you. Thanks again, and thanks for stopping by and for giving this.
Sure.
Very clear, because lots of us are not doing this type of, but I published a paper with one of my students some time ago on fingerprints, and was, I think, on the cover.
Yeah, I saw
of
that. Yeah.
No, chemical physics, but I think he's following Johan Tang. He's still working on extending this work in the more like neural network. So we invite him to come back and give a talk, because he has developed a statistics informed neural network.
Wow.
How you can learn fluctuations. So I think he's Zogren, when is Johan giving that talk?
I think very soon.
Very soon.
I mean, the next couple of weeks, yeah. And with Joaquin, one of
great.
Thanks again, Zogren. Maybe we can move on to the next talk, but thanks, Amir.
Sure. Thanks very much, George. I enjoyed.
Yeah, I just checked it. I think Johan is giving talk in 3 weeks. Yeah, 3 weeks later. So, okay. Thank you, Professor, for your wonderful talk. And let's move on to our second talk. Our second talk is given by Pipi Hu from Tsinghua University and the Yanqi Lake Beijing Institute of Mathematical Sciences and Applications. Pipi received his bachelor and PhD from Tsinghua University in 2014 and 2020. His research interests are mainly about differential equation related to machine learning, including solving PDEs with neural networks, operate learning for PDEs, and revealing hidden dynamics from data. So without further ado, Pipi, you may want to share your screen. Welcome.
Okay, thank you. Hello?
Yes?
Okay. Can we start?
Sure, go ahead.
Okay. Okay, thank you. Especially thank you for Professor Carnegie for the invitation. And today is a good day because it is Chinese Dragon Boat Festival. So best wishes to all of you. My name is Pipi Hu. You can call me Pi Square because I have 2 pi in my name. The topic I would give is about the revealing hidden dynamics from data, and I also want to give some introduction to learning the solution operators using the BiNet, but it's just a dish. Before the start, I want to introduce the background. The background is well known that machine learning has obtained great success, and the differential equations have been widely used. The past work illustrated that even a simple combination of the above two often yields something new. So there are some interesting work about the differential equation related machine learning. Some of the works are referred in the following. For example, inference PDEs, including the ODEs, including the Cindy PIN PDEnet. And researchers are also use the neural networks to solve PDEs or to construct the solution operator of the PDEs. For example, PIN, debris, and DeepNet. Other researchers also consider inferring the structure of neural networks by the ideas borrowed from the PDEs or ODEs. For example, the GCN neural ODE. The first work I would review, introduce is the review hidden dynamics from time series data. We call it the ODEnet to distinguish with the neural ODE. Here is the problem. Given that we have a time series data, YT, and of course the data has the noise. We denote the noise as ET. The text is, how can we find the hidden dynamics from the raw data? Or to be specific, can we extract the hidden ODEs from the time series data? we use the autonomous system of the ODE as the equation 1, dx dt equal f, where f is the linear or nonlinear smooth function from data. Can we find the function fx from the data to give the hidden dynamics? To that, we want to find the dynamics and we want to explain the dynamics. So the symbolic expression of fx is needed. A direct idea about the finding the f is the polynomial expansion. Of course, we can use other bases to expand the right term fx. Here we use the pth order of the complete polynomial basis lambda. It has the terms 1x, 1x2 to xdp. So the expansion of fx can be written as fx theta equal theta lambda. Here, fx become the linear combination of the basis, the polynomial basis. Thus, in the learning process, theta is a tunable parameters. And in our case, for the large noise term, the noise term E is also the tunable parameters. To review the hidden dynamics, namely, we want to review the optimal tunable parameters theta, we need to design the loss function. Here, we use the L norm of the L2 norm of the difference between the predictions and the data X. Also, we use the L1 norm of the theta for the sparsity. I would explain this one because this one is the main term, but we also have this one. This one is the L1 norm of theta. It gives the sparsity of the parameters. Because in the symbolic expression, we know that not all of the bases are actually works or actually plays a role in our run term. So we want the theta be sparse. So we add the panel here to make sure that the theta is sparse.
Pipi, I have a question. In equation 2, you imply that you will use this tensor product in different x1, x2 variables, right, in d dimensions. So that immediately hits you with the curse of dimensionality. So are you thinking of d something small, or d can be 10?
Sorry?
Little d, the way you wrote this, it implies that you'll run into the curse of dimensionality because of the tensor products that you're using in your basis. Yes. So you cannot use this for high dimensional inputs.
Yes.
What this 2 tells me, unless you change it later, that you will be limited to d, little d, the dimension, to something small, relatively small. Am I right, or you're looking at high dimension?
Yes, you are right, because the number of the bases is about the truth number p plus d choose d. So if the d is large, the basis number is very large.
Okay, thanks.
Okay, thank you. So I list the architecture of the ODE net. You can see the architecture, the left panel and the right panel. The left panel is the flowchart of the algorithm. From the start, we give the input is the training net, and we initialize the parameters, especially for the theta. And we randomly select M size batch, and from each point in the batch, we set it at the initial point, at the start point, and we use the ODE solver to integrate the differential equation, and we can get the successive predictions of the data. Now we compare the successive predictions and the data labels. We can get the loss. We minimize the loss and we get the update of the theta, and then we get another batch. So that's the whole procedure. B, C, D panels give the details about the procedure. You can see B panels actually tells us how do we choose the batch. For example, the black box is the batch, is the points in the batch. We choose 4 points in the batch because it is dim dimension. So there are many black boxes here. And the predictions, we use the ODE solver to integrate the ordinary differential equations, and we get the prediction successive predictions data. And we compare with the label, the data, we can get the loss L. And the D panel gives the basis expansion function, the value of the basis expansion. You can see that the lambda, the number of lambda is determined by the dimension D and the p order, the order P. And we want to find the proper theta because the basis is so many, and actually the right term is not so many, is not so don't use so many bases. So theta should be sparse. We first apply the ODNet on the health.
Excuse me.
Yeah.
Hello. This is Lulu for UPenn. In your figure here, you have in the D, you also have F as a network, right?
Yeah. We don't have a neural network. We just here to explain the right term, how the right term can be possibly expand.
Okay, but why this is called ODE net? So there's no net.
Because we call it a symbolic net, so we believe it is a net, but not neural network.
Okay, I see.
Okay, thank you. We applied the ODE net on the Lorentz on the data generated by a Lorentz equation. The Lorentz equation first started by Edward Lorentz in 1963 for the atmospheric convection. It has the 3 dimension x1, x2, x3, and it seems very simple. But interestingly, in some parameter regimes, the chaos comes up, and thus the data in the chaos regime is very difficult to learn. We summarize the learning text in the box called strange attractors of Lorentz equation. Our goal is to predict the strange attractors of Lorentz equation. That is, we want to reveal the hidden Lorentz equations, the coefficients from the data. The data is given by the time trajectories of Lorentz equation. In the chaotic regime, also we add 0.5% white noise. The setup is here. We use a complete polynomials up to the second order, lambda equal 1 to x3 squared, with 30 adjustable coefficients data. Because we have 3 equations, and for each one, we have 6 parameters. So we have 3 times 6 parameters to be learned. And the orbits are very sensitive to initial values. So they are divided into very small intervals to minimize the predicted errors. The learning process, the parameters data are optimized according to the procedure of algorithm 1. The sparse technique is taken. The result is that the correct form of Lorentz equation is reproduced with the maximum relative errors of coefficients less than 1%. The strange attractors are basically correctly predicted. We plot the results, and you can see in the figure A, the learner model is at the solid line, and the original model, the data from the original model with the noise is shown at the dot. You can see the learner model capture the most of the dynamics of the original model. To make it clear, we plot the x1 to t, x2 t, and x3 to t, the trajectories. You can see the learner model captures the most of the original model, but sometimes it misses it like this, because it's a chaos behavior, so it's very hard to reveal to capture the behavior. To our knowledge, the the result is the best of the literatures trying to review the hidden dynamics from the Lorentz system in the chaos region.
Oh, excuse me, for this case, what's your training data, the time domain?
The time domain train data is to about 25.
Okay, I see.
Also, we applied our ODNet on the experimental data. The experimental data, we use the acting aggregation. So what is acting aggregation? Acting aggregation is very important, and it is responsible for the contraction of the muscle cells and other cells. The mechanism of acting aggregation includes 3 basic steps: primary nucleation, elongation, and fragmentation. Primary nucleation means that we have 2 monomers and they combine together. That is the primary nucleation. And elongation means that we have a filament and 1 monomer added to the filament, and the filament becomes longer, so it is elongation. And fragmentation means that the filament may break up, so it is the fragmentation. The above processes can be explicitly transformed into a mathematical language of ordinary differential equations. So we have the data. The data is the experimental data. The data gives the varied filament mass MT for different total acting mass and different experimental conditions. For example, the first one is under the 40 mm KCl, and the second experiment is under this condition. We use 2 models to reveal the hidden dynamics also by the ODNet. The first one is the data-driven models. We have no pre-knowledge about the chemistry dynamics. We introduce MT equal M total minus capital MT to account for the M total dependence. Capital M is the filament mass. We have mirrored the mass in the experiment. MT is the monomer mass. We can compute the monomer mass by the total mass minus the filament mass. Thus, we can get 2 ordinary differential equations from the data: d capital M dt and dm dt. You can see the 2 differential equations is opposite actually. And the other model, we call it the physical-based models. With the general theory for acting aggregation, the number of acting filaments P also plays an important role. By introducing P, we can get 3 Carbonell equation. We call it the correct model. It's clear that P is actually hidden variable, and we don't have any data about P. It is a tunable parameter actually in our ODNet. We can train the 3 equations to find the coefficients from the data. Here is the learning results. The circles in the figure mean the actual data, and the solid line and the dashed line represent for the data-driven model and the physical-based model. We use the ODNet to reveal the hidden dynamics. You can see the models, the 2 models, both capture the dynamics pretty good, pretty well. The second work is the work that I want to focus on. That is, we want to use the so-called weak collocation kernel methods to faster reveal hidden stochastic dynamics from aggregate data. Before the start, I want to introduce the background. Stochastic data, there are 2 kinds of stochastic data. There are a lot of stochastic data, and we want to find the hardened dynamics. There are two kinds. One is the trajectory data, another is the aggregate data. Trajectory data is that the data, all the information of the individual data along the time are kept. For this kind of data, many methods exist, such as Hamiltonian neural networks, hardened Markov model, Kalman filter, and etc. But in the contrast, aggregate data means the trajectory of each individual modeled by the evolution of the state is not available. It means that you can't check the point along the time. There is no trajectory information. You only have the data at different time snapshots, a collection of data. They are not even the same number. For example, the expressions of the single cell DNA sequence and the data from the bird migration and the data from a social gathering, it is more general. For this kind of data, the existing methods are not very many. Chen and Liu in 2021 proposed a method based on PIN to use the density function, use a neural network to approximate the density function. And they use the PDE loss. They use the Fokker-Planck equation to get the PDE loss, and they use the KL divergence to get the dead loss. They train the neural networks and the parameters in the drift and the diffusion term. They get some results. And Zhou Haoming, they proposed the method in 2021. Also they use the Watson sense distance and by leveraging the weak form of the Fokker-Planck equation. It is still a hard problem to reveal hardened dynamics from the aggregate data. In this work, we want to reveal the hardened dynamics from the aggregate data. We call it the method is weak collocation kernel methods. We use the basic two fundamental methods is one is we use the weak form of the Fokker-Planck equation, and another is the linear multi-step methods. So let's define the data. Note that the real data set on discrete time T1, T2 to capital T as X. And XTJ in each time snapshot, the collection XTJ is the collection on that snapshot. And in each collection, there is XTJI. I mean the ith sample of that collection. That is, TJ is the jth time snapshot in the total T times. XTJ is the collection of the samples at TJ. And XTJI is the ith sample of the variable XT in the collection XTJ. We consider the general stochastic differential equation for the Brownian motion, dxt equal mu dt plus sigma dwt. We have to admit that the Brownian, for the general Levy process, there should be epsilon term. But here we only focus on the Brownian motion. Maybe this framework can be extended to that, but we didn't do that now. Here, xt means the xt is the d-dimensional random variable of the data. Mu xt is the drift term, sigma is the diffusion, and wt is the w-dimensional standard Brownian motion. It is well known result that the evolution of a density function txt of the random variable xt and the SE had the following relation. We summarized in the lemma 1. Suppose the xt solve the SDEs. The SDEs before this one. Then the probability density function pxt of a random variable xt satisfy the following d-dimensional Fokker-Planck equation. You can get it by Ito integral. Here, mu is the mu in the SDE, and d have the relationship with the sigma as d equal 1/2 sigma transpose. And we want to use the weak form of the Fokker-Planck equation. So we must get the weak form by integration with the text function. The text function we denote as psi x. It is independent with time t. It maps from the d-dimensional from the real space. In this work, we choose the Gaussian function kernel as the test function. The Gaussian function kernel, the d-dimensional Gaussian function kernel is very simple. It is multiplied by the one-dimensional Gaussian kernel. And x is the d-dimensional variable, rho is the expectation, gamma is the standard of variation. Also, the test function can be used in neural networks, but we focus on the Gaussian function kernel here. We multiply psi x, the test function, on both sides of the Fokker-Planck equation term and integrate by parts. One can get the equation 30. Note that in the equation 30, we transform we transfer the partial differential equation, partial differential operators from the density function p to the test function and psi. Here we have used the fact that psi and p vanishes on the boundary. As pxt, the density of the variable xt at time t, we can rewrite equation 13 as the expectation form and the equation 14, where E is the expectation over the probability density function pxt. Reminding that, note that we don't have anything about the pxt, but actually we have the data samples from the pxt. So here we can approximate the expectation form the equation 14 and the summation on the samples. We can get the equation 15. It is the approximation of the expectation. To make it clear and simple, we denote yxt, the summation of psi, the f, the right term of the equation 15, and we can get dy dt equal f. The equation 16 gives the relation of mu d and the data x. But we know that we don't have the trajectory data. So the data only gives at a discrete time. So d dt y xt need to be dulled. We use the linear multi-step method to deal the derivatives with respect to the time t. LMMS, linear multi-step method, is a well-known method for solving ODEs.
Pipi, I think you have your facts wrong in some of the references. Go to the next. For example, do analyze the multi-step methods that my group published in 2018. He didn't propose the methods. Also, I think you're missing all the literature that Yang Lu did on the Fokker-Planck, but also the same thing where you working directly with Gaussian and non-Gaussian noise, including fractional noise. So some of the, I don't know if you are aware of this, because some of the things that you're telling us is kind of done in the literature. But just one on this page. You're talking that Du Qian introduced linear multi-step methods. No, we introduced them in 2018. There's a paper well cited. So also, I noticed earlier you were saying some things that I don't agree. So I wanted to give you a warning.
Okay, thank you.
Please go on.
Okay. We use the linear multi-step method to deal with the derivative with the time. And etc. You at all, you apply the LMS in learning hydrodynamics with the equally spaced LMS, but the data are not always given equally spaced in time. So here we use a variable step size of the LMS in our work. For example, here is the list of the rules. We make simple conclusion that LMS and the equation 16 give the algebraic relationship between mu d and the delta x. So to reveal hidden dynamics, we need to give an expression of the mu and d. We use the complete polynomial basis to pick the order. The expansions can be mu I equal Zij lambda j, and the element of the diffusion term Dij can be Zij k lambda k. Here, Zij and Zij k are tunable parameters. So we have the linear system about the coefficient vector zeta, Ax zeta and Y hat x. Here, X and Y hat x are constructed by the big form. Zeta is collected and vectorized from the Zij and Zij k in the expansions of mu and g. A sparse linear regression is applied on the linear system by 3 steps. First, we just do the linear regression. Second, we shrink the parameters than the threshold given. And we remove corresponding columns of X and rows of Y hat. We repeat our process until converge. The sparse linear regression is proposed by Kutz in 2019. Here is the schema, the whole schema of the weaker collocation kernel method here. In the left panel, you can see the dynamics and its corresponding Fock-Planck equation. And the top panel, the delta x, and the top right is the Gaussian kernels. From the Fock-Planck equation and the delta x and the Gaussian kernels, we can get the weak form of the Fock-Planck equation. By the LMMS, the methods, we deal with the derivative with respect to the time. We can get the Y hat equal F hat. It is a nonlinear relation about the mu d and the delta x. So by expansion of the mu and d, we can get the linear system M zeta and Y M hat. Because we don't use one Gaussian kernels, we make collocations, and these Gaussian kernels will give different the linear systems, and we stack them together to combine to form a large linear system. I tilde zeta equal Y tilde. Here is the linear sparse linear regression. By the sparse linear regression, we can get that the zeta is only 8 of the zeta left, but all of the others vanishes. Here is the specific case, and we just list the result here. We first apply, we do some numerical experiments. The first is the stochastic equation with the Superman potential. Superman potential is a well-known potential in the quantum mechanics. It's like the hatch, like this one. And in the 2-dimensional, we calculate we want to find the hidden dynamics from the 2-dimensional data. So here we use the 2-dimension. It is like this one as the equation 23. The gradients we plot in the figure B. And the gradients give the drift term of the stochastic differential equation as 1424. The training data is we solve this stock SDE with the C11, C21, and the true number sigma 1 and sigma 2 here. And we solve this SDE over t equals 0 from t equals 0 to 250. We use the Ola-Malayama methods, and the time step is dt equals 0.001. We randomly choose 20,000 samples out of total 40 trajectories at per time snapshots. In the training setup, we use 200 Gaussian kernels as the test functions. That means we have 200 sublinear systems. We stack them together. And the expansions on fourth order complete polynomial basis with 15 times 2 plus 4, we have about 90 parameters to be determined. But you can see here, only 8 of them are real one. Others will be 0, should be 0. Here's the result. No redundant coefficients have been learned by our method. And the max relative error, MRE, is about 2.42% of the coefficients. Our algorithm run very fast. We run the algorithm on the MacBook Pro with M1 chip within 21 seconds. And the parameters is on the list. The second row is the true parameters, and the third row is the WCK, our method find. We also plot the dynamics using tools. We also plot the dynamics of the Fock-Planck equation with the learned parameters plotted in the S panel, and we compared with the true model B. The error shows in C. You can see the learned parameters capture the dynamics of the density evolution of the density function, and you can't tell the it is hard to tell the difference between the dynamics between the true model and the learned parameters. Figure C shows the errors. You can see the errors is about maybe 3 or 2%. We also applied the WCK method on the 10-dimensional problem. The text is we want to reveal the unknown drift and diffusion terms with n samples per time snapshots and m Gaussian kernels at time snapshots t from 0 to 1 of the 10-dimensional problem. The true model of the drift term is given by xi minus x minus x cubic, and the true diffusion is given as sigma equal 1 for each dimension. Here's the result of our WCK method. You can see if we use 10,000 samples and 1,000 Gaussian kernels, the result is quite good, but not good enough. But if we increase the samples from 10,000 to 100,000, the things get better. But if we use we can do more. We add more Gaussian kernels as the test functions. We use 100,000 samples and 10,000 Gaussian kernels. We can get the best result. You can see in the 10-dimensional problem, the solid line is the true drift term, and the dotted line is our learned drift term. Drift. You can see the learned drift term is around the true drift term, and the max relative error is about 4%. We didn't list here. We also applied the method to reveal the hidden dynamics for the 20-dimensional problem. We reveal hidden dynamics of the 20-dimensional case. Other conditions hold the same with the 10-dimensional case. N is the number of samples per time, M is the number of Gaussian kernels. The results are listed here. For the 10,000 samples and 10,000 Gaussian kernels as the test functions, we can get this result. And the solid line represented the true drift, and the dotted line also represents the learned drift term. You can see it's wrong, but the result is not so good. It's about 90%, more than 90% of the max relative error. And we increase the samples from 10,000 and to the 100,000. The things get better, and we have plot the result. The true is a solid line, and we have the dashed line represented for the learned drift terms. And this max relative error is about 20 to 30%. Here we want to mean that 30% error of the coefficients in that case doesn't matter a lot, because we do the experiment. We choose 2 dimensions of the drift learned, picked from the totally 20-dimensional case. We just pick 2 of them. C gives the third and fourth with about 10% relative error, and G gives the 10th and 19th with the 30% relative error. We plot the evolutions of the Fokker-Planck equation from the same Gaussian initial condition. Here, B is the t equal time 2, the true parameters give the result, the dynamics, and C is the learned parameters with about 10% relative error. You can see B and C. You can't. It's hard to tell the difference, and the error shows that it's about 5 maybe % error. Of course, if we give 30% error, you can compare this one and the true parameters and the 30% relative error parameters. They are very close. It is about 5 to 10% error. We also compared with the SOTA. Here we named the SOTA and the Chen's work. We compared with the set of the art SOTA, i.e. Chen's work. The true model is 1-dimensional case with the drift term. Mu2 is the x minus x cubic, and the diffuse term we choose sigma equal 1. The test is we want to review the unknown drift and different terms with 10,000 samples of xt at different time snapshots, i.e. the observations at 3 snapshots, they are equally spaced. B is the observations at 3 snapshots, but they are not equally spaced. We plot the results. And you can't tell very clear which one is better, but if we list the parameters in the table, you can see the WCK gets better. We also compare with the SOTA in the 3D and 4D problem. The true model is the 3D dimensional and 4D dimensional case with the drift term x minus x cubic and sigma equal 1 per dimension. The task is review the unknown drift and different terms with 100,000 samples of xt at the time snapshots for the 3-dimensional problem and 4-dimensional problem. The 3-dimensional problem, the max relative error is about 3%, and the computational time is about 3.6 seconds. And for the 4th-dimensional problem, the max relative error is about 7%, with a computational time of 6.1 seconds. And we plot the 3D problem and the results of 3D problem and 4D problems with the SOTA on the same figure. You can see the true drift term is denoted by the solid line, and the others, the WCK methods is around the true drift term. We make a conclusion. Here, I propose the WCK method. It is fast. It achieves a comparable accuracy, and it can be applied on a high dimension. And from the suburban potential, we can see that it can be applied on the complex cases. But it's not very enough. By the weak form of and the linear multi-step methods, we want to try to do more. We want to try to do more general form of the SD. As Professor Carnegie said, that the general form of the level process may correspond to the fractional Fokker-Planck equation. We can extend
the paper you mentioned by Chen, I think is from our group, right? Shaoli Chen, right?
Yeah.
Because all these results, I remember we introduced those benchmarks, the 1D, the 2D, the 10D, the 100, but So that's why you found that you were comparing with Chen, right?
Yeah. Because I don't have any benchmark.
Okay.
Yeah. We want to do real high dimensional problems, use other test functions and other approximations instead of the Gaussian kernels, instead of the polynomial basis. Because 20, maybe a 20 dimensional is high. If we distribute the data in the 20 dimensional, maybe in each dimensional, we can't get 2 points.
Can I just say one thing? Because in the paper by Chen, we had a representation like a polynomial, in which case, of course, you just find the coefficients, and that's very easy, like you're doing. But what we try to do is to make it general. So we also have a case where we didn't know at all the form, so we had a neural network for it.
Yeah.
And of course, that's more difficult to find, but it's more general.
Yes.
So okay.
So actually, for the 3D and 4D, the chance work also gave the polynomial the basis to approximate the mu and d, and they plot the curves on the figure, but I didn't get the data. So to compare with them, I get the data use the tool named get data digital from their figure. I just get every data from their figure and plot with plot the curves with us together. Here, we want to do real high dimensional problems. For example, in the real world, the image 1024 times 1024, it's far beyond the 20 dimension. It's about 1 million dimension. Maybe this work didn't work. And we want to find end-to-end auto refinement. Maybe the Watson distance of the two groups of the data, the samples can be used. Okay, finally, I want to introduce a dish that is solving PDEs using BiNet. We mainly focus on the solution operator. Most existing method for solving PDEs using neural networks. They use the neural network as an approximation of solution, and then use the optimization of the loss. Here, we propose the method combining a boundary integral equation and neural networks to solve partial differential equations PDEs. But the PDEs are limited to the PDEs which has the green function or the fundamental solution. And we learn the solution operators. Here, the solution U is given by the fundamental solution times the density function H and the integral on the boundary Sy. H is the neural network with tunable parameter theta, and alpha beta is the parameters of the PDEs. It is the coefficients of the PDEs, or it is the boundary parameters. We use the loss given by the boundary condition. We constrain the UX on the boundary, and the value is GX, so we can get the loss. The solution operators are naturally instituted. Here is the structure. You can see the omega beta and the PDE operator L alpha explicitly determine the fundamental solution G. But the operator L alpha and the boundary partial omega beta implicitly determine the density function. So for the density function, we use a neural network to represent the implicit dependence. And we multiply them together, integral on the boundary. We can get the solution U. By this boundary condition G on the boundary, we can get the loss. We minimize the loss, we get the optimal parameters for the theta. And now we can get the solution about U. It can be used to solve PDEs. For example, the Ablation equation I just put here. And it also can be used to map the boundary conditions to the solution, because the boundary conditions are encoded into the neural network. Here is a simple case. We just do some simple case here. The results are learning operators from boundary geometry to solution of the equation. We choose the triangle. The points, the vertices are the parameter, and we use the vertices of the triangle and mapping the triangles to the shape to the solution. In our experiments, 60% relative error of random triangles is less than 1%, and 98% are less than 4%. A result of typical triangle with vertices are shown in the right two figures. Also, we have to do some convergence result. We use the true of neural tangent kernel. I know that some students use the NTK kernel to analyze the pin. So here we also use the neural tangent kernel to give some convergence results of BiNet. The error in BiNet vanishes for double layer potential if we after fully training and the assumption also that the width of the neural network goes to infinity. The width of the neural network goes to infinity is a basic assumption of the neural tangent kernel. And for single layer potential, besides the conditions we also require the partial the boundaries partial omega is C infinity compact. Here is with the complex form of the kernel, we can get that the results still hold with the inner product defined in the complex space. Here's all the maybe in the next work we can study more about the boundary shapes to the solution. Okay, here is all the presentations, all the talks. Thank you.
Pipi, there's some references that I think you missed. There is a paper, you know, the paper of Shaoli Chen, which you compare. There is a paper by Yang Lu on and Daskalakis from MIT on the grand let me see on generative ensemble regression, learning particle dynamics from observations of ensembles with physics-informed deep generative models. There, we actually know, so we don't use at all the Fokker-Planck, and in fact, we can have unpaired and very limited observations. In other words, like the birds that you mentioned, right? You have a cloud, so you can have some snapshots of trajectories.
Yeah.
You don't have the initial density, and sometimes you may not even have the right pairs. So that's I think that's if you want to call state of the art, that's what you need to compare against.
Okay, I see. Thank you.
That's I can put this on the let me see if I can put it in the archive. Let me put it in the archive for you. But that was because I think that's really general, and I don't think people comprehend it. It's a little because it's a little different, but it basically uses GANs at some point. So okay. I just put it on the archive. But it's the most general case, I think, and I would invite you to check against those results.
Okay, thank you. Okay, I will check it. Oh, okay. Yes, we didn't find this paper. Sorry for that.
It was published 3 years ago, but.
Okay.
Also, I wanted to show you. Can I share my screen?
Okay. Sure.
George, I think you can share your screen now.
Okay. Let me see. Can you see my screen?
Yes.
Not exactly.
No, not yet. Maybe you can see it?
No, I can't see it. Oh, okay, I can see.
Oh.
Okay, so this is you see the date, January 4th, 2018. That's the multi-step.
Oh, okay.
This is the multi-step method.
Okay,
Duqian,
I
if you
see.
look at Duqian's paper, he analyzes theoretically which of these methods are stable and so on, because it has to do with the backward stability of methods. But this method was published in 2018. Now, I don't know how many references, has more than close to 200 citations, I think. But the interesting thing is that this paper was never published. It was rejected by twice by different journals, but it has 200.
Okay. Thank you.
So,
okay.
So this is just for your information. It's not Duqian. He's a good friend of mine. He's a good guy, but he didn't propose anything new. He analyzes existing methods.
Okay. Thank you for your reminder. I will check it and add the citation. Okay.
Do we have any more questions for our speaker? Oh, Matthew, go ahead.
Yes. So first, thank you for this interesting presentation. So first, I want to jump on this topic of Fokker-Planck. So I also would recommend not to follow this Fokker-Planck path, because I mean there are more problems than you maybe see at the moment. So, for example, since you have a density function, you must ensure the positivity of the solution. You must also ensure the normalization condition. And then there is a question of boundary conditions. I mean, you have a density function on an unbounded domain, so you need some artificial boundary conditions, which are very complicated. So if you really want to do this properly, there are a lot of open tasks to do. This was just a comment. If you really want to do Fokker-Planck properly. And there's one, if we talk about state of the art, there's one scheme that is called a Chang-Cooper scheme. But this is, how old is it? Maybe 30 years or 40 years. But this is a standard scheme for Fokker-Planck. Yeah, but it solves the first two problems I mentioned, but it does not solve the boundary condition problem. Okay, but my question was another one. In the last chapter, you showed this new approach of BNet. So solving a PDE by neural networks using, let's say, the Green's functions or the fundamental solution. And I mean, doing so, you are restricting yourself to a special class of PDEs. So the class, namely the class where you know that there exists a fundamental solution. Yeah.
Yes.
So from the theory, you can solve a smaller amount of PDEs. So maybe you can. I mean, what I was missing is what is the benefit of the approach compared to the usual PDE solver by neural networks?
Okay, because our BNet is focused on the typical problem. Actually, we use the framework to solve the unlimited PDE functions. It's different with the deep net or the F1O. So we didn't compare with them, and the solutions the benefit of the limited PDEs is that we can get more information into the structure. I mean that use the boundary integral method, and it is also useful because, for example, if we want to design the chips, we want to design to give the shapes of the chip. Maybe the problem Poisson equations can be used to give a good design. We can use that problem to solve the inverse problem.
Yeah, maybe the inverse problem might be a point. Yes, thanks.
Okay, thank you.
Do we have any more questions from the audience? George, do you want to say anything?
No,
Okay.
everything is good. Thank you very much, Pipi, for coming. I know it's very late in Beijing.
China.
And,
Yeah.
yeah, so happy Dragon Boat Festival.
happy festival. Thank you.
Yeah.
Thank you all.
No problem. So this is it for this week's Cross seminar, and everyone has a good weekend.